Hello, welcome back. And for this video on electricity, we're going to be talking about Coulomb's law. It, this is a very important law because it tells you, I told you that it's both an electric field and a force field. This law is what relates how much force do you get per charge. So point charges exert a force on one another. And I told you that negative repels negative, positive repels positive, and positive and negative attract. So these are going to be, we're going to be dealing with absolute value notation, and what you have to use is concepts in order to figure out, is it going to be an attraction or repulsion. If they're both opposite charges, they attract. If they're the same charge, they repel. And the magnitude of this charge, which interestingly enough follows the same format of the charge of gravity. Force of gravity is G mm over r squared. It's an inverse square law. Coulomb's law follows the same rule. It's a force of attraction and repulsion, just like gravity, but instead of being caused by mass, m1, m2, this is caused by charge, q1 and q2. Okay, and this value k is just a universal constant, which could be different in different parts of the universe. We don't know, but at least in our part of the universe, it's 8.99 times 10 to the ninth. And that is newtons meter squared per coulomb squared. It's basically just to cancel out all the other units. Okay? So we can figure out the force that two charges will exert on one another. For example, in a Bohr model of the hydrogen atom, the electron is in orbit about the nuclear proton at a radius of 5.29 times 10 to the negative 11th meters. That is our R. Determine the speed of the electron, assuming the orbit to be circular. Well, you're like, okay, well, this has force and K and R and Q. Nowhere in there does it have anything to do with speed. And okay, well, it's a little bit of a trick, but you still need to remember other stuff. Force equals something. Force equals mass times acceleration. So I could just as easily write this whole thing as being equal to mass times acceleration. And since this is centripetal acceleration, we know that centripetal acceleration also equals v squared over r. So even though we're moving on to other concepts, we're still falling back to these same equations. So if I solve that for v, I get v is equal to square root of f r over m. And I found that the force was k, 8.99 times 10 to the ninth, times q1 times q2. And since this is a proton and an electron, they have the same charge, and that charge was 1.6 times 1.60 times 10 to the negative 19th. Put that force into my other equation, and I solve for a velocity of 2.18 times 10 to the 6th meters per second. So that electron is going at about 1/100th or 1%, or in this, about a little bit under 1% of the speed of light. So it's not really going as fast as you might think. 1% of the speed of light, though, is still crazy fast. So this is if I have two charges coming together, all right? Well, what if I have, what's the force due to two or more charges? Like, let's get rid of that one charge. What if I just, this is the force between two charges, but what if I have charges out there in space and I introduce another charge to that space? What's the force on this new charge entering a space that already has force fields generated by other charges? So for instance, here, determine the magnitude and direction of the net force on Q1. So there's Q1 in the middle, Q2 on one side, and Q3 on the other side. Okay, that their charge is -4 microcoulombs, +3 microcoulombs, and -7 microcoulombs, and their distances are 0.2 and 0.15 meters. Now, since Q1 is positive, we know that the charge to that there will be an attractive force in both directions because the other charges are negative. So I need to solve for the Q1 Q2 charge force and the Q1 Q3 force, and then add them together, and that will give me the overall charge. Now this works because they're in a line. Guess what's going to happen when I take them out of line? So force 1, 2, kqq over r squared, force 1, 3, kqq over r squared. The force 1, 2 will be 2.7 newtons, and because of the positive and negative charges, that will be to the left. And force 1, 3 will be to the right. I add those together and I get positive 5.7 newtons per force. And in this case, positive is the positive x in my drawing is to the right. So there will be a positive 5.7 Newton force on that charge moving it to the right, which means it will accelerate to the right because there's a force acting on it. So I could even figure out what that acceleration is going to be if I know the mass. If I know the mass of that particle, I could figure out what its acceleration is by using F equals ma. Now, if the charges are not in a line, if they are in a plane, then it's not as fun because then you have to do x and y components of each interaction. So I give you some examples in the book and I will give you the answers to these questions. However, all I want you to understand is, so for this question, force 1, 2, 1, 3 is just going to be in a line, but force 1, 2 is not. And force 1, 2 will have an x and a y component. So you'll have to, step 1, break it into x and y. Step 2, do whatever math you need to do. You add the x's, you add the y's. Step 3, you take the x's and y's back together to find your net force. Now, I probably wouldn't ask you to do all that on the test, but I might ask you to tell me what direction that net force would be. So if you look at this drawing, you have a positive charge at Q1. Q2 and Q3 are both negative. So both of those are going to be attractive forces. So you should be able to figure out that the net force is going to be to the top right. It's going to be a northeastern net force. Okay. So that takes us to the end of this section. Not that much here, just Coulomb's law. F equals KQQ over R squared.